So knowing that we have a system of equations which is not square, in other words, a matrix which is not square, should be able to tell us something about consistency and inconsistency, and it should also tell us something about uniqueness of solutions versus non-uniqueness of solutions. So we have kind of 4 different categories here. If I have a system of equations which has m rows and n columns, then let's consider the case where the number of rows is greater than or equal to the number of columns. So I have more rows than I have columns. That would be the taller than it is wide case. So let's sort of draw a picture next to this here. Taller than it is wide. Then what did we say about the consistency, consistent versus inconsistent, about this set of equations? Since it's not possible for us to have a pivot in every row, it's possibly inconsistent, right? There always exists some right-hand side that will make this inconsistent. So there is always is inconsistent for some right-hand side. For some choice of B. In other words, there are no matrices that are taller than they are wide for which AX equals B is always consistent. We're going to reframe that in a couple of chapters into a statement about the column space. In other words, the image, the range of the linear transformation represented by this matrix would span all of the codomain. But for now, we're just going to think of it as a statement about equations, that if your matrix is taller than it is wide, if it's an overspecified system, then we can always find some right-hand side that makes it inconsistent. All right, but then what about uniqueness of solutions? If a solution exists to a linear system with more rows than columns, can that solution be unique? So let's imagine I have a pivot here, and then maybe I have another pivot right here. Then would the solution of that system of equations be unique or not? Why not? Would we? What do the variables correspond to in a matrix again? Columns. And if I have a pivot in every column, then it is unique because I don't have any free variables. Remember, the pivot columns are the bound variables. The non-pivot columns are the free variables. So it is possible, again, if we have a full set of pivots, in other words, one in every column, then solutions, when they exist, will be unique. So we do have an if in this box, but that's okay. Because for systems that are at least as tall as they are wide, we can get uniqueness of solutions. In order to get that, though, we have to have a full set of pivots. If we're still missing a pivot column, then we're definitely going to get non-uniqueness. But it is possible for every column to have a pivot when the matrix is at least as tall as it is wide. So uniqueness is possible here. Whereas consistency is not always possible. So now let's talk about the other situation, where our matrix is at least as wide as it is tall. So this would be m is less than or equal to n. There are at least as many columns as there are rows. So what do we know about, let's start with the uniqueness side this time. What can we say about the uniqueness of solutions to this system? even if I have a full set of pivots. That's right. So a full set of pivots is going to fill up all the rows. But it cannot, if we are wider than we are tall, fill up all the columns. So in this example, as long as we have more columns than rows, so maybe I should be extra careful here. If I want to make this table as useful as possible, let's just restrict ourselves to a rectangular system, so m strictly greater than n or strictly less than n, so that our square matrices are not on this table. So as long as I have more columns than I have rows, there will always be one column, at least, that doesn't have a pivot. And so there is always a free variable, one or more free variables. So what does that mean about our solutions?
Not unique.
Not ever unique. Because in order to be unique, we need a pivot in every column, and there just aren't enough columns for that in a matrix which is wider than it is tall. So uniqueness is an impossibility for these. What about consistency? In our example here,
It'll be consistent.
always consistent. How come?
Because there's, there'll always be a B. Wait.
Remember again, consistency is a question about rows in our matrix.
Yeah, so there'll be, there's a pivot every row, so
There-
it'll always be consistent.
There's a pivot in every row, therefore every equation has a bound variable in it. And so we don't get a 0 on the left-hand side after our row reduction. So we can't ever get 0 equals 12 or something like that in this example, if we have a full set of pivots. Then we're going to have a pivot in every row. And therefore this linear transformation is onto. Therefore, we will have a system of equations which is always consistent. So consistency for every value of b is a possibility over here, but only if we have a full set of pivots. If we still don't have a full set of pivots, if there's still a row with no pivot in it, then we can still make that system inconsistent. But as long as we have a full set of pivots, we're okay. So this is kind of a classification for what can happen with rectangular systems of equations. Because whenever we have more rows than we have columns, or more columns than we have rows, we're either going to be in a situation where uniqueness is always not possible, so wider than tall, where we have an underspecified system of equations. We will always get at least one free variable, and so solutions will never be unique. And meanwhile, on the other side of the table, if I'm taller than I am wide, if I'm overspecified, then that system of equations can never be consistent for all choices of right-hand side. We can always pick some right-hand side vector that will make it an inconsistent system of equations. So those are the two where we can always say something really strong. That a tall system is always going to be inconsistent for some choice of right-hand side, and a wide system will never have unique solutions.